automatic operation of today's machinery requires the use of switches that may be activated by the movement of the machine. The repeated accuracy of the switches, reliability, and the response of the switch must be practically instantaneous. The operating force, stroke, size, and mounting are critical factors in the choice and installation of limit switches. This is in part due to the mechanical limitations of the machinery. It is also essential to carefully match the electrical rating of the switches with the loads to be controlled. Generally, the operation of a limit switch begins when the movement of the machine or a moving part of the machine strikes an operating lever that actuates the limit switch. The limit switch in turn will affect the electrical circuit controlling the machine or a portion of the machine. Limit switches are pilot devices in the control of magnetic starters and relays. Their function may be to start, stop, reverse, slow down, or speed up the electric motors that operate the machine. Limit switches may be used as normal operating devices, or they may be used as emergency switches to prevent the improper operation of a machine or process. They may have momentary contacts, spring returned, or maintained contacts. The contact symbols shown here are the NEMA symbols for normally open and normally closed limit switch contacts. Another type of limit switch, which is often used in different types of control applications, is the micro-limit switch or microswitch. Microswitches are much smaller than conventional limit switches. This small size permits them to be used in small spaces that would not be accessible to the larger devices. Another unique characteristic of the micro-limit switch is that the actuating plunger requires only a small amount of travel to cause the contacts to change state. Electrical ratings for the contacts of micro-limit switches are generally 10 to 15 amps at 250 VAC. The basic microswitch can be obtained with a variety of activating arms. The sub-miniature microswitch operates in a similar manner to the micro-limit switch. Sub-miniature microswitches are approximately 1/2 to 1/4 the size of a microswitch, depending on the model. Because of their reduced size, the contact rating of sub-miniature microswitches ranges from 1 to 7 amps. Proximity sensors are increasingly becoming popular in a wide range of industrial applications due to their versatility, reliability, and inherent safety. It is possible to use proximity sensors in applications where mechanical limit switches prove inadequate. Proximity sensors can be used to replace limit switches in most applications. They can be used to detect the presence or absence of almost any material without touching the material. Because proximity sensors are solid state, they are extremely reliable, operate at high speeds, and have inherent application and design freedom. Inductive proximity sensors detect metal objects only. Most all inductive proximity sensors are RF, radio frequency inductive devices that operate on the ECO, eddy current killed oscillator principle. These types of sensors usually use a tank circuit tuned to the frequency of the oscillator. The sensor head contains 2 coils, thus forming a small transformer. When the tank circuit is tuned to the frequency of the oscillator, current flow around the tank loop is high. This will cause high voltage to be induced into the secondary coil of the sensor head. When metal is placed near the sensor, the inductance of the coil increases. When the coil inductance changes, the tank circuit is no longer tuned and does not resonate to the frequency of the oscillator, causing current flow around the loop to decrease. Capacitive proximity sensors do not depend on metal to operate. They will sense virtually any material, such as concrete, glass, wood, plastic, paper, and even liquids through a sight glass. When an object or material is brought in to the proximity of a capacitive proximity sensor, a change in capacitance causes the sensor to gate a switch. The primary disadvantage of these types of sensors is their limited range. Most cannot sense objects more than 1 inch, 25 millimeters away. These types of sensors are able to operate in a wide range of voltages, such as 2 to 250 VAC or 20 to 320 VAC. Ultrasonic sensors operate by emitting a pulse of high-frequency sound and then detecting the echo when it bounces off the target object. These sensors may be used to determine distance to the target by measuring the time interval between the emission of the pulse and the return of the echo. Many of these sensors put out an analog output voltage signal. The value of this signal determines the distance to the object target. Photosensors are fast becoming the most popular means of industrial sensing because they are safe, versatile, reliable, and may be used on applications where other types of mechanical sensors cannot operate. The no-touch concept is often the only reliable means of satisfying a switching requirement. In this capacity, they are similar to proximity sensors. Photosensors are able to detect targets moving into the sensing field from any direction and in virtually any sequence. They are used to detect the absence or presence of almost anything at a considerable distance. Because photosensors are solid state, they are capable of operating at high speed, they are reliable, and they have a long life. Photocells whose resistance changes with light intensity are referred to as photoresistive or photoconductive. When light strikes the cell, the resistance of the cell decreases and current is allowed to flow through it more easily, thus creating a light-sensitive switch that can be used to operate a load, in this case, a pilot light. Direct scan requires that the light source and the photoreceiver are positioned opposite from one another so that the light source shines directly at the photoreceiver. The object to be detected passes between the light source and the receiver. If the object is opaque, the direct scan will yield the highest signal ratio and is normally the best choice for the application. As long as an object blocks enough of the light, it may be tipped or skewed in virtually any manner. A general rule of thumb is that the object size should be at least 50% of the diameter of the photoreceiver lens. An alternative is to fit the photoreceiver lens with an aperture similar to that found on a camera. This aperture will reduce the lens diameter. Direct scan does not rely on the reflectiveness of an object or that of a permanent reflector, so no light is lost at the photoreceiver. For this reason, direct scan allows you to scan farther than reflective scanning. Direct scan does have limitations. Alignment is critical and difficult to maintain where vibration is present. Also, with a separate light source and receiver, there is the additional wiring and expense. This type of control is also available using fiber optics. Reflective scan sensors have the light source and the photoreceiver built into the same sensor body. Mounting restrictions and limited space sometimes prevents aiming the light source directly at the receiver, so the light beam is reflected either from the target itself or from a permanent reflective target, such as shown above. Retroflective scan has the light source and the photoreceiver in the same sensor body. This is often referred to as a retroflective scanner. The beam of light is directed at a retroflective target, acrylic disc or tape, which returns the light beam along the exact same path that it was sent. A larger target reflector will return more light to the photosensor, allowing increased scanning distance. Alignment is not critical with these types of sensors. The light source photosensor may be up to 15 degrees either side of perpendicular to the target. Because alignment is less critical, retroflective scanning is an excellent way to counteract vibration. Retroflective scanning can be used at distances up to 40 feet in clean air conditions. As distance increases, a larger retroflective target should be used to intercept and return as much light as possible. Single unit wiring and decreased maintenance are also advantages to this method of scanning. This type of control is also available using fiber optics. Convergent beam scanning is primarily used to detect objects that are only a few inches away from another reflective surface. It is the best choice for edge guiding or positioning of clear or translucent materials. It is also a good choice for position sensing of opaque materials. Convergent beam scanning is dependent upon the optics of the sensor. The light beam is simultaneously focused and converged to a fixed focal point in front of the sensor. The sensor is blind a short distance before and beyond the focal point. This makes the sensor an excellent choice when highly reflective backgrounds are present. The sensor senses light reflected back from an object. The graphic above shows a convergent beam sensor detecting parts from above while ignoring the surface the parts are sitting on. Specular scanning requires that the surface being detected be constructed of shiny material, such as rolled or polished metal, shiny plastic, or other highly reflective materials, such as the hard hat that the man is wearing in the graphic above. With the shiny surface, the angle at which the light strikes the reflecting surface is equal to the angle at which it reflects from the surface. Positioning of both the light source and the photoreceiver are critical. The distance from the source to the surface and the distance from the surface to the receiver must also be consistently controlled. If they are not, the light will be lost due to improper angle. The size of the angle determines the depth of the scanning field. This makes this type of scanning an excellent choice for use in fill detection, such as controlling the level of a liquid in a vessel. Diffuse scanning uses light to detect the proximity of an object. Matte surfaces, non-shiny, such as wood, rubber, cork, dark plastics, etc., absorb most of the light directed at them. The light that is reflected is scattered equally in all directions. Because the light is scattered, a very small percentage of it actually reaches the photoreceiver. Therefore, scanning distances are limited to approximately 6 inches. Alignment is not a critical factor with diffuse scanning. This type of control is also available using fiber optics.